anymore.
All right, this seems to be the time. So let me start here real quick. I would like to first welcome and wish everybody a happy new year. We start here the new DS series. Sorry, let's go back. On the online SPICE and SPIN+X seminars organized by Spin Phenomenon Interdisciplinary Center SPICE, led by myself, of course, and Karen Reciprocity, and in collaboration with the Collaborative Research Center of SPIN+X, which is led by Martina Schliemann, Burkhard Hillebrand, and Matthias Chloe. As everybody knows, or most people know, this is a Zoom webinar system where please write your Q&A during the talk, and then I will moderate it afterwards. It's always on Wednesdays at 3 p.m. And the attendees are muted, and I will moderate later on and allow you to talk. If you cannot talk or have no microphone, I will ask a question for you during the Q&A after the talk. And just please keep in mind on the next talks will be next week the Bernabé, then comes to us Hermans, and then Oleg Sakov, Chernyshov, and then we will continue that filling up the program afterwards. Just a quick intro. Bart van West really does not need introduction in our field. He's a world-renowned physicist. Made his name in mesoscopic physics, actually discovering something that many people are very puzzled, and this, this zero bias anomaly is something that he actually discovered in these nanowires a while ago. And in the last 2 decades, he's been the pioneer in mesoscopics and nano spintronics, with many aspects that he's pioneered. And then not only that, he's received many prizes, but one of the ones that impressed me the most that he's a knight a Dutch knight. So I think we should call him Sir Bart. So with that, I'll stop my introduction, and I'll ask Bart, please go ahead and share your screen. And yeah. Very good.
Let me see, where am I now?
Perfect.
From beginning.
Perfect.
So
Yeah.
you see it now, right?
I see now. Go ahead and start. Thank you.
Okay, thank you. Thank you for the invitation, and also thank you for a very nice introduction. I just want to get rid of my of this video thing on the right. How do I do that? Oh, I minimize it or hide it. Small. Okay, now I have the small one.
Okay, yeah.
Okay, now I have the small. So thank you for inviting me, and thank you for this nice introduction. I want to say, well, in the next 45 minutes, a little bit about chirality induced spin selectivity. This field has been in the air for about 20 years. And the surprising thing is that still a lot of what is being done, what is being measured, what is being made in this area is not understood. And this is a little bit strange, in my opinion, because we are talking obviously about spins, about spintronics, and we are talking about combining it with chiral systems. In most cases, these are molecules. So of course, the transport in molecules is different from transport in metals or semiconductors, but not that different. Huh? So we got interested in this field. I need to find my cursor. Just a second. How do I? Oh, wait a minute. I will pick a cursor here. Here I have it. About some years ago, and we started to do experiments, basically combining graphene, transport in graphene, spin transport in graphene with chiral molecules, which are basically deposited on top of the graphene. And this was and still is a collaboration with Ben Veringa from our university. But we soon found out that we had a lot of questions. So we started to think about it. And we wrote basically 2 papers, which are about the modeling of charge transport and spin transport. And basically those papers I would like to use as a guideline for this talk. So the work which I'm going to present is actually the thesis work of Xu Yang. He has written a very, very nice thesis, in my opinion. And I am also asking him to send the thesis around to people. So if you are interested in a copy of this thesis, please send me an email and I will forward it to him. And last but not least, there is an important contribution from Casper van der Waal, who spends most of his time as the director of our institute, but still has a little bit of time for science. So I'm going to introduce chirality, but I'm also going to introduce something which is called false chirality. And of course, it's strange. Why would you now introduce a concept and then a false concept? But it turns out that this false chirality also plays a role in a slightly different one. And I will try to make that clear. Then I will say a little bit about some of these experiments which concern electronic or spintronic transport of chirality induced spin selectivity. I obviously have to make a selection, and the field has been started by Ron Naman, who has a very active group at the Weizmann Institute. So I'll show a few of these experiments, but I will also use them to highlight what is now special about these experiments and what is now not understood. So we actually set out in how can we now understand well, one class of these experiments, and these experiments measure the magneto-resistance. So chirality-induced spin selectivity is obviously a way in which we can couple charge transport to spin transport. And one way, of course, to measure that is to use a ferromagnet, either as a polarizer or an analyzer. And if you do that, you should be able to measure a spin valve type of magneto-resistance. And that is what is measured in these experiments. But as we have shown in our modeling, this is not allowed in the linear transport regime. And there is a very important phenomena or concept which is called reciprocity, which plays an important role. So I will describe how we do that. Then I will show, this would be a sad message, right? I mean, a description that something cannot work or doesn't exist. However, if you go to the nonlinear regime, it becomes possible to detect chirality, or let's say chirality-induced spin selectivity in these type of experiments. And I will show you the relatively simple trick which you can use. Then obviously, the question is, if I have chiral systems, could I also use them in some fully non-magnetic spin valve? And the answer is yes, you can make spin valves, but now not with ferromagnets, but with chiral molecules. So I'll show you how that works. Then there is the important discussion, and I have explicitly written two-terminal. So what is the difference between two-terminal and multi-terminal devices? And it turns out that there is a crucial difference, which I like to point out. Then I will conclude with some open questions, right? And I will tell them what they are. And what is very relevant, and probably I don't have too much time for that, is to mention a few experiments where chemical synthesis and self-assembly of chiral molecules is actually being affected or being controlled by a magnetic field. And this is, of course, a very challenging thing. And let me see what I can say about it. So chirality in nature. So this is a flower. You can already clearly see that it's chiral, because of, maybe not so clear, because you can see that this one overlaps this one, and this one overlaps this one, and this one overlaps this one. So the most straightforward manifestation of chirality is obviously a helix. You have two types, left-handed and right-handed, and you go through it. And here you have to turn anti-clockwise, and here you go clockwise. And of course, an obvious feature of this thing is that if you try to do the same thing from the other side, you go in the same direction, right? So you see that really these helices can be distinguished by their chirality only. There's more to be said. Chirality turns out to be important aspects in chemistry and in biology, because nature is actually chiral. A lot of proteins have a specific chirality of one type, and which is actually also based on the chirality of amino acids. So which you somehow can understand. If you have a certain chirality, it might want to connect better to molecules of the same chirality of the opposite chirality. There is also a warning. So if you want to make a medical drug to do something positive, be careful that you use the proper chirality, because this one is not well known for causing all sorts of health problems. And an important aspect of that is that it's related to the chirality. So one one enantiomer is the one which should do the positive ones, and the other one does the negative ones. So again, that is a nasty thing about chirality. This is, I want to show this one. It looks a bit complicated. To be honest, I got it from the internet, but a thing is called the gyroid. So I think this is made by some kind of a, how would you call this, structure, and then either synthesizing molecules or molecular assemblies. I'm not quite sure what it is, but the point is, of course, if you look through it like this, you see clearly a anti-clockwise chirality, right? Because if you proceed, you turn anti-clockwise. So this for the red one, and the purple one obviously is a clockwise one. So this one contains both chiralities. And the interesting thing is that if you now look at it from this perspective, from the front, or you look at it from the right, or if you look from the top, you see the same chirality, right? So that means that chirality is not a vector; it's a scalar, right? You could say these guys have a, let's say, a plus chirality, the other one have a minus chirality, so the total chirality is 0. But you can easily imagine that if you remove these guys, you have a system which has a specific chirality. Okay, so there are many things known how chiral systems interact with, for instance, light, because you can, of course, make circularly polarized light. It propagates in one direction, as you could. So actually, you could even say it makes some sort of a helix in space. So this is definitely a true chiral property, which will interact with the chiral medium, and it will actually do so. For instance, the clockwise polarized light can be transmitted. The other one is attenuated, or maybe it's sent in a different direction. So this is a clear interaction between a true chiral physical concept and a chiral medium. But I should say that this is being done. Definitely, it's not being done in something like a linear transport regime, right? So it's clearly a non-equilibrium effect. This experiment is not the original experiment, but is actually the experiment which triggered quite a lot of interest in the field. So we have a gold substrate. We actually assemble DNA on it with some linkers, and we can have right and left helical DNA, and we can come in with light, and we can actually measure the spin polarization of the spins which come out. And the most important experiment is what you see here. So here, the molecules are actually, these are chiral molecules of one type. And what is done is that what should I say? You're not seeing this window, right? I hide it. What you see is actually that the polarization of the electrons which come out depends on the polarization of the light. Right, so you might say, well, this is a bit of a complicated system, but in any case, this gives the impression that you can actually create spin-polarized electrons by having non-polarized light. I should emphasize this, maybe non-polarized light and going through this helical DNA. So I am not going into all these discussions of symmetry, space inversion, and time reversal. I would like to go immediately to what is now CISS. So we have two helices of different chirality, and then immediately the remark which you can make is that the spin direction, well, either aligned in this direction or the opposite direction, that is not a chiral property, because you can already say the chirality was a scalar, and the spin direction obviously has a direction. So it's a vector. So it is not enough to produce interaction with your helix, helical molecules or whatever you have. You need also a velocity, right? So then definitely, what is CISS is basically that. And if we wanted to measure this in electronics or in spintronics, we expect that spins of a certain direction, let's call it right. I call them right spins because that is the spin direction. Right spins going to the right will go through this one. Left spins going to the left will go through this one. And here we have the same, but then opposite. Yeah. So this is very relevant because these helices or these chiral molecules, they don't break time reversal symmetry. Yeah, because a spin up can go in this way, and then a spin to the right, but then in order to go that way, you need a spin to the left, right? And the combination of these actually does not break time reversal symmetry. It's different from a ferromagnet, because then a spin right can maybe go through this way, but then also the spin right can also go the opposite way. Yeah, so that is a very different symmetry. So I'm not going to say much about this false chirality. It turns out that, and let me just give you the conclusion. And so I mentioned that the electron spin moving in a specific direction, parallel or anti-parallel to the spin, is a chiral property. So it can interact with chiral molecules or chiral enantiomers. A magnetic field is called falsely chiral. And now we have to be extremely careful what I'm saying, because to be honest, this definition is maybe not 100% clear, but it can in principle not distinguish chiral enantiomers. The same is that the combination of magnetic and electric fields, well, that the magnetic field cannot do it is clear, because a magnetic field is a vector, and we needed a scala property. But you might imagine that you have a magnetic and electric fields, but again, that does not work. And this was described in quite some detail by Bart, but we have to be careful here. Yeah, so again, we are interested in interaction. How can we study the interaction between charge and spin currents, which are coupled by a helical system? So that is what we understand. How can we measure it as a magneto-resistance? Yeah, so let me start with the symmetry, which I already mentioned. The symmetry for creating or coupling spins and charges is different in a helical system, in a chiral system, as compared in a ferromagnet. This is a very beautiful experiment. Let me immediately put on everything, which was done some time ago by Ricken and co-workers. And what they had, I'm not sure what was actually the material, but what they did is they passed the current through a material, and they measured the voltage, so they could measure the resistance. And now they played a trick. So they applied both a magnetic field as well as a twist. So they made a twist in the system, right? They could twist, let's say, clockwise or anti-clockwise, so they could actually make this material chiral. And then they measured this resistance. So they found that there is a magneto-resistance, which is basically which scales, which is basically gives you a background resistance, and a component which scales linearly with the current and the magnetic field, or the dot product. So this is obviously a non-linear response effect, because it is a correction to the resistance which depends on the current and the magnetic field. So you see that the dot product of the current and the magnetic field, current direction, also gives you a scalar, right? So this is an example where chirality and a magnetic field can still produce an effect, but it can only do this in the non-linear transport regime. And I will come back to that later. Okay, these are very beautiful experiments which have been done over well, almost 20 years. Let me just explain what is being done here and what is the surprising element. So what we have here is a nickel. It's all on the substrate, but what is relevant is a nickel layer, which is magnetized by a perpendicular field, either in the up direction or in the down direction. You need a certain field for it, half a Tesla or something, and then your magnetization is up, and then you go to down. So they can compare their measurements with an up magnetization and with a down magnetization. Then they want to assemble molecules on this. And as you know, of course, this is sometimes quite often done by sulfur, by thiol groups, which will nicely attach to gold. So they have put on a layer of about a few nanometers of gold. Then they assemble the molecules on top of it. This definitely is not such a nice orientation as it's here. It's usually a bit of messy thing. And then they have a AFM, where they can actually control the force with which they push this tip into the molecules. So they do this with a controlled force, and then they start measuring IV, right? And what you see is that this is already an average. So there's a lot of statistics because they have to repeat this experiment. But the very surprising result is, if you do the statistic correctly, you find that there is a large difference in the current for magnetization up and magnetization down. And you see that here the magnetization down current is the maximum, and here the magnetization up current is the maximum, and but that what has been done is the helicity of these molecules has been changed, right? So this is of course already very surprising, because in my opinion, I am not aware, maybe you can think about it, of any magneto-resistance or magneto-transport measurements where there is still an effect. Whereas I have nickel, I have gold. This is not an ordered layer, and so basically, if this is related to exchange, it still has to work over a considerable distance. I don't understand that. So this is one question I have. I also don't understand why this polarization is so large. Yeah, because if you interpret this in terms of spin polarization, you get numbers which are of the order of 50%. And that is strange, because the spin polarization of nickel is already lower than that. Right? So how can you get a spin polarization which is bigger than that? It gets even more surprising, because there's a very recent experiment which was done in a collaboration between the group of Ron Naman, who actually did these measurements, and Bert Meijer from Eindhoven University. Bert Meijer makes can make large supramolecular structures, and he can make them out of chiral molecules. So this is actually what is being done. Right? They're very big. And then he can also control the chirality, but also the amount, let's say the concentration of chiral molecules. And what is seen is that if you increase the concentration, you can go up to magneto-resistances close to, well, I mean, this is what is shown. For Mach up, you get this. For Mach down, you get this. And if you translate this in a magneto-resistance value, you get something very almost close to 100%. This is even more surprising. I don't understand that, to be honest. And I want also to indicate that an important question is, how does this polarization depend on the bias? Yeah, because I already mentioned this Ricke experiment, that if you have a large bias, in principle, you can have an interaction between a magnetic field and a chiral system. And now these measurements are a little bit confusing, because we have looked at the data in more detail. It turns out that the spin polarization at low bias is more or less constant. Yeah? So we have a relatively big range of bias voltages where the spin polarization is more or less constant. That is also very surprising. Okay. How am I doing with time, Jaro?
Quite okay.
So there are two essential questions which sometimes gets mixed up. We had some trouble in pointing out what we are going, what we are, well, actually what is our claim in our paper and what is not our claim. We are not. We have not looked into how CISS is generated in a chiral molecular structure, right? So we have not addressed the question, what happens if you send the current through? Does this current become spin polarized? This has been the subject of many, many papers. I mean, hundreds of them almost. This is not what we are doing. We are just accepting the fact that the CISS effect, meaning the coupling between spin and charge current in these molecules, is there. But we are going to address the issue, how can we measure this in a transport experiment? Because this is our simplified version of the transport experiment. I have a metallic, non-magnetic, non-spin polarized electrode on this side. This could be this platinum tip, or sorry, this could be the substrate. I have a ferromagnet. I have a chiral component, and on the other side, I have a tip which is also non-magnetic. So I'm interested in the transport from a non-magnetic electrode to a non-magnetic electrode. And I want to ask the question, how is that changed when I change the direction of the ferromagnet? Yeah? And for that, we are going to make a model, which I describe in a little bit detail. We are actually going to decompose the circuit into two elements. One is a ferromagnetic element. It's actually going to be a tunnel junction. That is going to couple spins, spin current and charge current. As we know, of course, if we use a ferromagnet, which is a polarization of 30%, we expect that the spin current will be 30%, well, the current will be 30% spin polarized. So this is the conventional ferromagnetic element, and this is the chiral component, which we also have to describe. Yeah. So we're going to ask the question, what happens if we start to evaluate this system? So what are the issues? Let me go back. Then there is an important theorem which I should mention here, and this is actually based on Onsager reciprocity, but it has been written down for mesoscopic transport systems by Marcus Buttiger, who unfortunately passed away already some time ago. And he actually pointed out that if I do a two-terminal measurement, so I have electrons starting from one electrode and going to the other one via some system, that the two-terminal resistance, defined as the voltage drop divided by the current, can change as a function of field, but it has to be symmetric when I change the direction of the field. Right? And you can understand this a little bit, because if you have a two-terminal measurement, you look at the electron and you apply a field. Of course, the electrons will go from the left to the right, doing their typical cycloton orbits. And you can also make them again go back from the right to the left. But then you have to, in order to use the same orbits, you have to invert the field. So that symmetry, combined with the fact that you do the thing in linear response, because that is important, because if you know that there is a way to get from left to right, you already know, because of linear response, there is a way to get from right to left. You already know that also. That actually results in this famous reciprocity theorem. This is for two-terminal. If you have 1, 2, 3, 4 contacts, two current contacts and two voltage contacts, you get the same. But then you have to invert the current and the voltage contact. So if you think about the Hall effect, I suggest try it for yourself. And you will indeed find that if you interchange current and voltage leads, you get the same value, but you also have to change the direction of the field. So this is a very important theorem. Also because it's not only about the magnetic field, it's basically also about the magnetization. So everything which breaks time reversal symmetry and which actually can be written as some vector like a field, a magnetization, that should basically obey this theorem. So that means that for our system where we had one ferromagnet, we have no spin, we don't have a spin valve, we just one ferromagnet, and the experiment basically inverts the direction of the magnetic field, then it actually implies, and the magnetization, then it implies whatever system we have connected to it, chiral, non-chiral, you name it, there should be no change in the resistance in a two-terminal geometry in the linear regime. So let's see if this works. So what we are going to do is we are going again, this is a model again. We have the electrode on one side, and we characterize this by a, well, electrochemical potential, Fermi energy you could call it. We do it on the left. This is not spin polarized, so you could say the Fermi energies for spin up. Well, when I say spin up, of course I mean spin in this direction, because this is the only relevant direction of the spin. But I use it up and down because it's easier. But if you talk about up, I'm talking about this spin. If talking about down, I'm going that one. So for spin up and spin down, the Fermi energies are the same. The same also here, but obviously we can have a difference between the Fermi energies between here and here, which drives the current. Then we have introduced a node, and we have assumed that this node is going to randomize the direction of motion of the electrons. That's one. Second of all, it is also going to introduce inelastic scattering, meaning that you are supplying electrons from this side at a certain energy. You're also supplying, or taking away electrons from this side at a different energy. So in general, if you do not include inelastic relaxation, you get a distribution function, which is definitely not a Fermi function, but we have now assumed that there is inelastic relaxation. So we get, again, the distribution of the electrons is a Fermi function. We have assumed that the temperature remains the same, but of course, the Fermi energy itself will be different. It will be somewhere in between the Fermi energy on this side and that side. So that is one thing. Second thing is that we will also induce a spin accumulation. So the Fermi energies of the spin up electrons and the spin down electrons will be different in general, right? So this is our system, and we're going to analyze it. So now comes the interesting thing. Can we now understand that this system does not produce a magnetoresistance? And normally the idea is the following. I pass a current through, well, there is this charge spin coupling here. So I'm going to introduce a spin accumulation here, right? So again, charge current goes through the chiral system. There is a spin current. It will actually introduce a spin accumulation here. And the spin accumulation can actually be picked up by the ferromagnet, right? So that is actually the process where the spin injection is by CISS, and the spin detection by the CISS element, and the spin detection is by the ferromagnet. But of course, we are also doing at the same time, because the ferromagnet is spin polarized, otherwise it would not work, and we pass a current through, so we are injecting a spin current here, right? Yeah, and the spin current indeed again makes a spin accumulation, but the spin accumulation is actually going to produce a charge current or a change in the charge current, because we have this spin charge coupling, which works in both ways. And the outcome of this is again not surprising, that these two processes exactly cancel, and we have no MR in the two-terminal linear regime. Yeah. So let me say a little bit about how we started to think about this problem. This is a bit of a artist impression. So this is our chiral element. We have simplified this in a way that basically the spins, well, I still call them spin up, but spin up electrons can go from here to here. Spin down electrons can go from there to there, right? According to the property of the chirality. Now, so we're going to again keep track of the Fermi energies of the spins. So this is if I have a non-polarized electrode, these are the same on this side and these are the same. However, they can also be different if there is a spin accumulation. Right? So what is the consequence of that? Well, okay, so we can come in with the good spins, they go like this, and here from they go like this. But what happens now to the bad spins, the ones which are not going to be transmitted? Well, they are going to be reflected, but you can actually show, and actually that's based on current conservation, that in this process, the spin of the electron is flipped. And this is already known from spin-orbit interaction in two-dimensional systems. And you might say, okay, if I introduce a spin-orbit field in a 2D system, for instance, by the Rashba effect, so that basically means I can make a constriction. So maybe I can transmit spins in one direction and I can reflect, because they can go over the barrier, and the spins in the other direction, they cannot go over the barrier. But in that process also, the spin has to be flipped. So this it's basically a consequence of well, it's inherent in this process, right? So what we're going to do now also is, so we have how many driving forces do we have? Well, you might say I have 4, yeah, but in reality, of course, I have only 3. Because if you have the system in equilibrium, all these Fermi energies are the same. And if I then shift all the Fermi energy by a certain amount, I am not going to change the current. So in reality, of course, I am only interested in 3 of them. And so that is what we are now going to do. Yeah. I will not go into the technical details. If you like, you can keep track of what is happening to the individual spins. So there is a spin up coming in here. And in reality, of course, it will not be fully reflected. It can be transmitted, can be reflected. So we can describe this entire problem in terms of transmission and reflection matrices. That is a rather complicated thing. But let me just focus on what we get at the results. At the result, we get something which looks like this. So we have driving forces here on this side, and we have responses as a charge current, which is obviously conserved. And we have spin current, which of course does not have to be conserved, because these processes, obviously, they flip the spin. And if I have a molecule which is not symmetric, they don't have to be the same either, right? So I have to basically relate these currents, the charge current, spin current flowing on this side, spin current flowing on that side, to the driving forces. And of course, we have elementary, this is the charge voltage, the difference in the Fermi energies. Yeah, and of course you might say, how do I define μL? I take the average of the spin up and the spin down Fermi energies. That is going to give me the charge electrochemical potential, and I'm going to take the difference between them, and that I call μR, and that is the spin accumulation or the spin chemical potential, right? So this is just rephrasing from the up-down picture to this picture. It's not fun. It's not important. But if you look at it, you might say, okay, so these are conductances. Yeah. So this is actually the conductance of the device, right? Because it tells you how the current changes when I change the voltage. These are the spin conductances, right? So they're telling us, okay, how does this spin current depend on the spin accumulation on the left? Well, this is the The same for the right. And I have taken here a symmetric molecule, but I don't have to do that. Now you might say this is all very interesting, and what can we learn from it? But there is a very important rule, and it is called reciprocity. If we, and we already mentioned one manifestation, if we write down this in using normalized currents, and we normalize the current so that we actually talk about number of electrons per second, and we basically we remove the charge and we remove the spin. If we do this in a normalized way, you can actually show that the off-diagonal elements have to be the same. Yeah? Because the process is, this guy, for instance, would be the current which is generated by a spin accumulation on the left, right, which is then produced by the spin charge coupling. This guy is the spin current on the left generated by the voltage across the system. So these are related via the microscopic processes which couple it, and they have to be the same in the linear response. So this has to be the same as this one, this has to be the same as this. So you have a matrix which is, it's basically a symmetric matrix. So let's do this analysis. So here, since we have this system, we can already make the system a little bit simpler, because we only are talking, we need to know the current and the spin current, and we only have we don't have spin accumulation in the reservoir. We don't have it here. We only have it in one side, so we can make it a bit simpler. So we can describe this ferromagnet as actually a tunnel junction. The response of this ferromagnet, the current as well as the spin current, which actually is flowing into this node from the ferromagnet, we can write it like this. Then you find you have diagonal elements, which are basically the charge conductance and the spin conductance. Don't worry about the minus sign. This is a consequence of the convention. But what is very relevant is that, again, I see this off-diagonal element, and here I see that they are opposite. And that is the consequence of the fact that this is a ferromagnet which is polarizing the spins. And of course, PFM is the polarization of the ferromagnet. So if I switch that, this element goes from positive to negative. So I have either a negative element here and a positive there, or the opposite way. Yeah. So that is the way how the ferromagnet or the ferromagnetic tunnel junction makes itself known to the spin and the charge transport in this system. So what about the chiral system? Well, we can do more or less the same. Again, we have off-diagonal elements, and here you see that because, I mean, charge transport and spin transport is not exactly the same. They are not exactly the same, but that is not so important. But now you see that the off-diagonal elements are the same, right? So this is a symmetric matrix, and this is an anti-symmetric matrix, right? And this turns out to be crucial because it's not so difficult to now do this calculation, and I will be a bit fast here, where you basically describe the ferromagnet by this matrix and the chiral system by this matrix. I should basically say a little bit more that there is we actually have not put anything in this, no strange assumption. We are simply writing down a thermodynamic response matrix in terms of the driving forces and the possible currents. And then we look at this matrix and we look at the symmetries which are imposed by reciprocity, because this clearly, this clearly obeys reciprocity, because if we change the direction of the field, this matrix, the sign of these elements is reversed. So you can actually show that obeys the rules. So we have not done anything, no strange assumptions, simply this transport matrix. So then you will not be surprised that if I now measure the two-terminal conductance, I find that it only depends on, it's a complicated expression, so I'm not going to give it, but it only depends on these matrix elements squared and these ones. So there is no coupling between these two matrix elements. So that basically means that if I change the magnetization, then I would go from minus G21 to G21, and this goes from G21 to minus G21. It has no consequence on the conductance, which basically was the result we already anticipated. So no MR in the linear regime. And now comes the beauty, in my opinion. How can we now, we still would like to say something about the chirality of the system, right? So how can we do it? But now I'm going to show you this one. And it takes let me be careful what I'm now doing. So I am modeling the ferromagnet. I have assumed that in the ferromagnet itself, there is no, the spin up and the spin down chemical potentials are the same. And I can do it because this is a metallic system. I am making a tunnel junction. So most of the action is across this tunnel junction. So I can basically assume that this ferromagnet is basically in equilibrium and it's characterized by this chemical potential, which is the same for spin up and spin down. There's only one chemical potential. Then I am drawing the barrier. So this is a typical barrier. I have to go up. Yeah, I go through an oxide layer or whatever it is, and I go back to here. I have to be careful. Yeah? So I have applied a voltage difference across this barrier, right? And now you see where you are also going to distort the barrier, right? But that's not the most important reason. What you can clearly see is if you look at electrons from this side, yeah, they see an effective barrier, right? Electrons from which arrive here, they see a higher barrier, right? So these are the electrons which actually go from the ferromagnet to the chiral system or to the node. So what can you say about this? Well, suppose this ferromagnet is spin polarized, then I expect that the spin current will still be a specific fraction of this current, because it does not matter how easy these electrons can go through this barrier, right? You know, of course, if at all energies the spin polarization is the same, which does not have to be the case, but we assume that it is. For each 10 electrons which go in, we have 7 with spin up and we have 3 with spin down. So the spin injection process does not depend on the energy. The spin detection process is actually very different, because the result of this is that I'm going to make a spin accumulation. That means I had a difference between the Fermi energy of the up and down. Well, now let's look at how these will basically, what are they going to produce? Well, we get more spin up and we get less spin down. They have to go through this barrier, but they see a relatively big barrier, right? And that is simply because now we're only considering the effects of states which sit here, whereas for the injection, we are considering the entire range, right? So you clearly see that if you go to this nonlinear regime, yeah, the process which couples the injected spins to the injecting current is not affected, but this process which actually translates a spin accumulation into a current is affected. Yeah, so that means if we go back to this matrix, I'm not sure if I have it here, that these diagonal elements will no longer be the same, right? So we have basically destroyed this nice symmetry. In this case, we have done it for the tunnel junction. Yeah? And if we do that, it's not a big surprise. We can actually calculate now for a typical system, what is the current which flows as a function of the bias, and you have the blue and the red curve for different direction of the magnetization. You see for low bias, there is no difference. There is no MR. But for high bias, you start to see a difference between the blue and the red one, right? And again, that is why, because you have destroyed, or you have, well, not destroyed, but you have basically affected this nice symmetry, which is no longer fully there. You see now that the MR, and this is a crucial remark, is anti-symmetric, right? It is odd, because here well, let's say the magnetization up has a higher current, but here the magnetization down has the higher current. So if you plot the magneto-resistance of this system, it is actually changing 0 here, and it's changing sign. And then you notice that this is exactly the same or comparable to what I wrote, what I discussed about this Ricken experiment, right? There we also have, in principle, in the linear response, no MR, and we start to produce an MR if we apply a bias current. In this case, it's bias voltage, and this MR changes sign. How am I doing with time? How much have I left?
So you have about 15 minutes or so.
Oh, 15 is fine. Okay. So now comes an issue that I also want to explain. Now we have our chiral system, and the chiral system obviously is a molecule. We're going to assume it's a molecule. Yeah. So now, how to model transport through molecules, and we had quite some discussion with the referee, and I think it was a justified discussion because we are making a simplification that we have a HOMO orbital, which is then in equilibrium, is occupied. We have a LUMO orbital, which is not occupied. and we want to address the question, how do electrons go through this system? We don't have to do that in the linear response regime, because, as I said, this matrix is very elementary, and this reciprocity holds whatever you do. I mean, whatever type of transport experiment you have. But in the nonlinear regime, this can matter. So we have said, okay, let's make a non-interacting electron picture where we can still consider the transport as the transmission of carriers which start on this side. How do they go through the system and end up here? And on this side, of course, how these carriers which are transmitted here go up there. And we assume that their energy is conserved. So then you might already say, okay, we have a bit of a problem here because we have the LUMO and we have the HOMO orbital. You could, in principle, also make a semiconductor model out of this, by the way, by assuming that there are also states available above the LUMO and below the HOMO. That does not really change the picture, but you might say, hey, wait a minute, this is a problem because these electrons which start here, there's no state available here, right? So in principle, they cannot go through. And of course, that is not correct. But because you know that if you look at tunneling, you know that if you, in a naive way, you could say, okay, the wave functions of electrons which enter here will decay exponentially if you go from here to here, and the decay length will depend on how far below the LUMO you are. So the further below the LUMO you are, you could say naively, I need to borrow more energy, which is only allowed for a shorter time or a shorter length scale. So there is definitely a, let's say, sort of tunneling process to go from there to there, right? But this tunneling process will depend very strongly on the energy, right? Because, as I said, I mean, the closer you go towards the LUMO, the bigger the transmission will be. And of course, if you sit exactly at the LUMO, you will have some resonant transmission. So we have an energy-dependent transmission. That is the thing we need. Now you might say also, okay, is there another way to do it? Well, the other way is simply to use the Fermi energy. Then there is no energy-dependent transmission, but there is an energy-dependent occupation. That gives you exactly the same result. And the reasoning here is exactly the same as we did with the ferromagnet. We assume that we have this chirality induced spin selectivity coupling, which is there, and we assume that that does not depend on energy. Of course, in reality it will, but okay. But then again, we have the same argument that if you look at the current, let's say, if you look at the current which is produced by this bias or the spin current, it is actually carried by energy and electrons in this interval, right? If you look at, so that is actually going to produce, let's say, the spin current, which flows as a function of the voltage bias, and that is not. But here we are talking about the effect of spin accumulation on the current again, but that is actually that's generated by states which sits close to the Fermi energy. And so that these are different energies, and clearly, if you are in the linear regime, you are using the same energies to go from here to here and from there to there. So this effect is nicely symmetric. But if you go to the nonlinear regime, it again becomes asymmetric. I forgot to mention that this idea we basically also based on idea of Ronnie Janssen, who actually also, but now for semiconductor systems, actually showed that you can actually break reciprocity or change the sensitivity of ferromagnetic tunnel junctions if you go to the nonlinear regime. In any case, here we have the very similar mechanism. So this is now a calculation where we assume that the ferromagnet is still nicely in the linear response regime, but now the chiral system goes into the nonlinear regime, and you see more or less the same effect, right? You see again, of course, no magnetoresistance at low bias, and we get a symmetric or anti-symmetric magnetoresistance again in correspondence with the Ricken experiment. In reality, of course, I have to say that this model is highly simplified, but the symmetry arguments still remain. So this should also hold if you really have coherent transport. Hey, I have to maybe, that's an important remark, so I should, okay. Here, what we have assumed is this inelastic relaxation. Why do we have assumed this? Because if we are using electrons which conserve their energy over the entire system, then for each energy, this reciprocity rule holds. So then we will not get a magnetoresistance. It's crucial for this effect that the electrons which are actually tunneling through the ferromagnet and which which are going through the chiral system have a different energy distribution. Yeah. Now you might say, okay, so if this would be a coherent system, what is going to happen if we don't have this explicit? Of course, in reality, you don't have this explicit node. But then I expect that if you go through a system, an electron goes through, at some point it will indeed experience some inelastic relaxation. So there will be instead of putting everything in a node, it will be more or less distributed in the entire system in a complicated way, but it will basically produce the same effect. So then I basically already anticipated this. So you could say, okay, if the transport is carried by states which are close to the LUMO, then of course, if I raise the energy, I am increasing the transmission from left to right. But then if you are sitting close to the HOMO, then if you lower the energy, the transmission is going to be increased. So now it turns out, and this is an important conclusion, that here you can clearly see it. Here we have done a calculation where the transport is actually carried by states close to the LUMO and the HOMO, and you see that with the same polarization of the ferromagnet and the same chirality of your chiral system, you have an opposite magneto-resistance. So very important thing is that the sign of your magneto-resistance, which you can actually measure in the nonlinear regime, depends on the chirality of your molecule. It depends, of course, also on the spin orbit, sign of the spin orbit interaction, because the chirality is not enough, of course, to describe the interaction with the spins. You also need to know, what is the sign of your electric field. But it also depends on the direction of the ferromagnet, and it depends on the specific states you are using. So it's a rather complicated analysis. So then let me make the next step. Then you might say, okay, two-terminal doesn't work. It can only work if you are going to the nonlinear regime. That's a bit of a pity. But of course, if you have followed the symmetry argument, you might expect that if you take two elements which have the same symmetry, so two chiral elements, right? And then you switch one to from a right-handed to a left-handed, you're actually making a chiral spin-Wolf. And you can actually, now this is the calculation we did, you can actually show that indeed that again produces a spin-Wolf effect, because the symmetries of these systems are the same. And you can clearly see it here, although it's small, but I mean, that depends on the parameters. Well, it depends on what you call small. You clearly see already spin-Wolf effect at close in linear response, and that is going to be changed. And you see already the difference in the compared to the ferro chiral system. Here there is no sign reversal. It has the same sign on both sides. So it would be very nice if somebody could make such a system, and we are actually working on this. So you have a spin-Wolf system which does not have any ferromagnet at all. This I basically already described. Anti-symmetric symmetric doesn't work. Anti-symmetric matrix works because this is, of course, the conventional ferromagnetic spin-Wolf. Symmetric also works because there was a difference between this one and this one. Now there is a slightly different manifestation. You could say, okay, let's send a current through a system which has no ferromagnet. It's just a barrier, just to transmit the electrons. Then I go through the chiral system. Well, if there's current goes through the chiral system, I'm going to produce a spin accumulation here. And what about if I start to interfere with this? I'm going to apply a magnetic field. And the spins are polarized in this direction or in that direction. So if I apply a magnetic field perpendicular to it, I am going to introduce Larmor precession. So if the field is big enough, I'm going to basically delete the spin accumulation. Then you can actually show that there is a difference indeed. So there is an effect of this field, because in one case you had a spin accumulation here, which created an additional contribution to the current. And in the other case, if the field is big enough, there's no spin accumulation anymore. So this produces a magneto-resistance. And then you might say, well, this is contradicting what you said, but it doesn't, because this effect does not change if the field is up or down, right? If the spins are polarized in this direction or that direction, does not really matter if this one makes a precession like this or makes a precession like this. The effect on the component of the spins in this direction will be the same. So that does not contradict this theorem. it might even be a way to detect chirality, because you don't need a ferromagnet anymore. You just use the effect of the magnetic field on the generated spins. And we are basically writing down a proposal on this. Okay. Can we do this entire thing in the multi-terminal devices? And the answer is yes, because I think it was already discussed here, that in this particular case, although there is no magnetoresistance, there still is a change in the spin accumulation, right? And this you could, in principle, measure, right? Not in this geometry, because there is no, eventually, if you change the spin accumulation here, it's going to change the voltage across the ferromagnet, and it's going to change the voltage on the chiral system in the opposite way. But of course, if you would attach another ferromagnet here, and you would use that as a voltage probe, then indeed you could see it, right? So if you have if you do a 3-terminal measurement or a 4-terminal measurement, you can, in principle, also measure CISS in the linear regime, right? And this is a little also related to this paper, which actually describes also the effect of spin-orbit interaction in semiconductors on spin transport, and also emphasizes that 4-terminal or multi-terminal measurements can allow you to see it in the linear regime, and 2-terminal systems should not produce any magnetoresistance. Okay, this was demonstrated in an experiment which uses a metallic system. This is by the Japanese group of Yamamoto. They pass a current through like this, and this is a chiral system. So that means that they are going to produce spins which are polarized in the direction of the current. And so we have, again, spins which are polarized in the plane, either in this direction or that direction. And then this spin accumulation which is happening is being picked up by the spin Hall effect. So there is a heavy element, platinum, I think, strip on top. These spins actually polarized like this, they go up like this, and according to the conventional, to this detection technique, they produce a current or a voltage perpendicular to this. So this is a true 4-terminal measurement, right? Because I have sending a current through, I am producing a voltage between the point here and here, right? So this is perfectly in agreement with this theorem. And they have also checked that if they also have, of course, with spin Hall effect, you have the inverse spin Hall effect. And so then they interchange the current. And so here the current produces the spins via the chirality. And then the spins are going to be converted back into charge by the inverse spin Hall effect. I should be careful what I'm now saying. This is the inverse spin Hall effect. Here it's the opposite way around. So I'm sending a current through. I am producing a spin accumulation at the interface via the spin Hall effect. That is going to produce a voltage because of the spin charge coupling of the chiral system, right? So here we have basically the CISS is producing the spins and is basically picked up by the inverse spin Hall effect. Here the spin Hall effect produces the spins, and it's actually being picked up by the inverse CISS effect, which of course have to be related. And this is of course a very crucial element of our analysis. Okay, let me then come a bit to the end, but I'm not completely finished. Linear response to terminal magnetoresistance due to CISS must be zero at or close to zero bias. How do the experiments behave? They don't all want to obey this rule. Yeah, so that's already strange. And I can think about several reasons, but I think if you have a fundamental theorem, it's a fundamental theorem, right? Either it does not work or it works all the time, right? So I don't see any reason why now this chirality induced spin selectivity would try to mess with this fundamental theorem that the two-terminal measurements, electrical measurements, cannot produce a magnetoresistance. So I've shown you that you expect that the first order correction, as a function of the bias, there must be a generation of NMR, but it has to be odd in the bias. Yeah? And then it could be more complicated if you start to involve different orbitals, but the first correction should be bias odd. Yeah? And if there are deviations from this, then we have to really start thinking. So let me Yeah, so again, I already showed you that these experiments are, first of all, different on the molecules, are difficult to do in the linear regime. However, we have some data which actually shows that this magneto-resistance persists, which is the magneto-resistance actually is not odd, it's even in the system, but it persists to low bias. So it seems to contradict these statements, and that I don't understand, to be honest, right? So what are we doing? I mean, we are currently trying to get some more understanding of this, also experimentally. This is very important. These experiments are being done also using statistics. It's not that you measure just one molecule and then you change the magnetization. No, you will first measure a lot of molecules and then you change the magnetization. And for each configuration, of course, there is a difference in distance between the tip and the molecule. So there is a difference in overall conductance. So you have to use some average technique, and there you have to be very, very careful. So then, of course, the way to measure this directly in the linear transport regime is to use a multi-terminal geometry, and I have already given you one example. We are currently doing something like this. We are using ferromagnetic spin pumping. We are using our famous guinea pig material, yttrium garnet, because it's a magnetic insulator, or it's a ferromagnetic insulator. We are going to apply a magnetic field. We're also going to apply a microwave field. So we're going to induce magnetization precession. And that means we can, if the magnetization is like this, we can actually pump spins from the YIG into the chiral layer. And then again, you already know it by now. If I do that, I am going to basically favor, since if I inject spins, they have the tendency to go to the right or to go to the left. That means that I'm going to produce a current between two electrodes, and which can be picked up as a voltage in an open voltage circuit. So you could say this is a little bit a different manifestation, a similar manifestation as the spin Hall effect, where you inject electronic spins. Well, you inject, they're still electronic spins, but they are then coupled via the spin-orbit interaction, via the spin Hall effect. Here, of course, the CISS itself is also some sort of spin-orbit interaction but it definitely has a different symmetry, because here the spins, the current direction we expect to be the same as the spin direction, whereas for the spin Hall effect it is perpendicular. There is one. I would like to leave you here with this one, which is, I think, the most surprising of all of them. These are experiments done, several papers also done by the group of Ronda Maan. What they are interested in is in the following. If I have a chiral molecule and I'm going to apply an electric field, then obviously I am going to change the nature of the states, right? I will have an electric field. I'm going no. So then their claim is that what is happening then is, of course, the chiral spins in a chiral molecule by themselves are not magnetic. There is no magnetic moment. But they are claiming that if I apply an electric field, I am going to make a magnetic moment. And they claim that they measured it like this. So I have a whole bar geometry, right? I mean, it's basically on a substrate, doesn't matter. So they pass a current, let's say, between source and drain, and they measure the voltage. So that one detects the magnetic field, the perpendicular magnetic field, somewhere at the bottom here. And then they assemble, again, molecules on it, chiral molecules. And then they apply a gate voltage. So the gate voltage is not producing a current. It's only producing an electric field in this direction. So either up or either down. So that is what they do. And then they measure the whole voltage as a function of this gate voltage. And they do it for molecules with different chirality, right? And also opposite. And these are typical measurements which they get, and they interpret this as being produced because they measure a transverse voltage. They interpret this as a Hall voltage, which is generated by the magnetic field, which is again generated by the induced magnetic moment in these chiral molecules. And we have several problems with that because this Hall signal corresponds to an average magnetic field of 10 millitesla. So that's already huge. And André Geim has done very nice experiments to use graphene, or the Hall effect in graphene, to get information about the magnetization of material which is deposited on top of the graphene. But he measures only maximally 0.2 millitesla, and that is because, of course, of the demagnetization of this thing. If you have a magnetic layer which is magnetized, well, it does not really matter in what direction, but even if it's magnetized in a perpendicular direction, the field lines which will go out have to come back again because they are closed. So in a very thin, extended thin film, there should be no magnetic field outside the film, even if the magnetization is up or down. So that is already, so we don't know what is going on, but I would like to give it as something to think about it. Is it in principle possible that if I take a chiral system and I look at the magnetic moment in that system and I apply an electric field, so I'm going to change the nature of the states, is it possible that this chiral molecule will develop a magnetic moment? And I have not yet found the proper answer that this is not possible, so, but I would still like to know what you think about it. Okay, now I think I should summarize. Already did it. We have used symmetry analysis to emphasize the difference of spin charge coupling in a ferromagnet as compared with a chiral system. Well, that means that two terminal MR must vanish and must appear as bias odd with increased bias. You can detect it in a linear regime, but you have to use various multi-terminal geometries. For your information, of course, we will have our nice workshop again, our GRC workshop again, hopefully, if Corona does not prevent it in the Le Diable. There is now a new series starting on chirality induced spin selectivity in August. So if you are interested, please have a look. Okay. I would like to stop here.
Oh, thank you very much. Everybody can raise their hands to clap for you, the 300 of you that showed up. So thank you very much. We'll now begin with the questions, and I'll start maybe with Amit. Let me get Amit here and allow him. I'll unmute you.
Can I just make one remark, because I forgot to mention it. I forgot to mention it. So we have seen, and this is very interesting, that if you go beyond the linear regime, yeah, even elements which are non-chiral, like a magnetic field or a magnetization, can actually affect the physics or the transport through a chiral system. Right? But you have to go to the non-linear regime. And now Ron Aman has showed, and I think he really has showed, that he can affect the synthesis or the assembly of chiral molecules on a surface with a magnetic field. And this is certainly not understood. But what we know is, of course, that since this magnetic field is not a true chiral entity, we cannot do this experiment in the linear regime. So in chemistry, you might also think about linear regime, because what does that now mean? It's the regime where you do not actually change the microscopic processes. You only, let's say, offer more material, a higher concentration of one material, which will be converted back into the other material, but essentially using the same chemical processes. So that is the equivalent of linear transport in the chemical sense. So then to match these things or couple them, it must mean that if you are in that regime, there should be no effect of the magnetic field. But if you go away into a non-linear regime, there might be an effect. So I think these surprising results are not contradicting themselves, but to be honest, you have to think about a mechanism by which a magnetic field itself can affect chemical processes, and that is I think already very different. So I wanted to say this also, maybe that to stimulate the discussion.
Okay. So Amit, go ahead and ask your questions.
Thank you. So thank you for the wonderful talk. So I have actually two questions. One is in the beginning you were talking about helicity as a scalar, right?
Yeah.
But the trajectory of the electron itself in the helix, you can treat that as a vector. So isn't that enough for a vector-vector interaction?
No. Let me go here. Wait a minute, just go back. Just go back to, oh, now I have here. You can see it now, right? I'm sorry, my slides now, yeah?
Yeah.
Yeah, this one, right. No, I am, there's two things, right? If you, so this is my statement. If you want to have a process which depends on chirality, Yeah. Yeah. So you need, first of all, you need two systems which are actually chiral, right? Here this helix is chiral, right?
Mm-hmm.
So this is if you look at this helix, it's chiral. If you go this way, you see that there is this rotation. A spin by itself is not chiral, right? But a spin which moves is again a chiral quantity, right? So there can be an interaction between the chirality of this helix, which is actually this property, and the velocity of the spin. Yeah, because that is another. But then again, it can only depend on the product of the velocity and the spin. Yeah.
Yeah. Okay. It feels to me like there's some kind of equivalence. Anyway, we are short on time. So the second question is, in a quantum wire, one can separate or let's say decouple the spin current from the charge current.
Yeah.
Can you think of a mechanism which can do the same in a chiral system?
That's what this experiment is basically about. I mean, this magneto-resistance experiment, right? Yeah, because I'm not quite sure. This is what it's about, but it's crucial. Yeah, although of course we cannot measure the spin current. Well, I mean, you have to measure it in it has to have some sort of manifestation. Let me go to here. Yeah. And here again, it's measured by generating spin accumulation and being converted back into a voltage. Yeah. So if we do an electrical,
yeah, you want to, but if you can decouple them.
I don't know exactly what you mean. You want to have a pure spin current.
Well, that's the question. Yes.
No, you can. No, you can. Let me go back to the other one. No, that's a very good question. So here the idea is that we generate a spin current, a pure spin current, because the YIG is an insulator, right? And we are basically injecting a spin current in this direction. So that's a pure spin current, which is generated by the spin pumping in the YIG. If we now send, and that produces a charge current and a voltage. If you send now explicitly a current through this chiral system, it is going to produce a spin accumulation here, a uniform spin accumulation, which actually will generate a spin, try to generate a spin current also in this direction. So then the charge current goes like this, and the spin current goes like this. So the answer is yes, it's possible to do experiments, right? Yeah. So where you basically produce 100% spin polarized current using CISS.
Okay.
But it's not a crucial thing. Whether it's 100% or 90%, it actually does not.
Yeah, that's the thing that you're addressing. So let's go to Tero. Maybe Tero, would you like to ask a question?
Yeah, thanks, Bart. It was very stimulating talk. The question that I had actually in the beginning already was that is there an angular momentum transfer related with the current across the chiral molecule? And if there, I mean, or let's say is there an absorption of the angular momentum by the chiral molecule? And in other words, is there a torque on the molecule?
Yeah, so the answer is that's an interesting question, and the answer is we have not addressed that. I think it would be very interesting to also look into that, because we have only used spins which are nicely either polarized into the right or polarized to the left. Yeah, and to be honest, we have used let's say we have used a description where it really does not matter how these chiral molecules are actually aligned. Let me go back to this plot. So basically, this was my remark also, that if I pass a current through like this or like this, right? You might say these electrons are experiences this entire helicity, but it should also be that if you pass a current like this, the same effect should also be there. Yeah, because it's so. However, it will maybe have a different magnitude. Yeah. So yes, I think there can be effects of spin torque, but then I think you have to go to the next step. Here we did not really we were not taking into account how actually the current goes through like this or maybe like this. We actually didn't care because it will only give a numerical difference. If you if you want to talk about torques, then I think you also have to worry about the orientation of the helices relative to the current. Not probably does not fully answer your question, but because I don't see how
it was an ill-defined question, but I was just wondering if there is a torque on the molecule, what is the equivalent of the Landau-Lutschitz-Gilbert equation?
Yeah, it's a good one. In any case, there are processes which produce spin relaxation, or spin flip. Yeah, they have to be there, but that is basically spin flip. That is I think slightly different from spin spin precession or spin torque.
Yeah, that was we lost. So let's go to Julie Nazarov.
All right, thank you. Hi, Bart.
Hey.
It's rather a remark. First, thank you for promoting Gonzaga relations to wide audience. It's really thrilling to see that even in 21st century, one can do so much about this. Chirality is quite old stuff. Let me make a remark about something which is was known for a while, but I guess it's rather useful for you. You said that magnetic field is a vector. It is not quite so. It is pseudo-vector.
Yeah, pseudo-vector, yeah.
Right. What does it mean? It means that coefficient of proportionality between current and magnetic field is sensitive to chirality.
I'm not 100% sure what you mean with that one.
It's a coefficient between vector and pseudo-vector. Pseudo-vector times chirality gives you vector.
Yeah, but I mean, I think it's not so. It is not so different from what I mentioned, right? With this Ricken experiment, yeah, that if you take a look at the correction to the resistance, if I apply a current, there is a term which gives you a correction which is proportional to the current.
No, it's different. So in principle, there could be current at 0 voltage, which doesn't make sense. If
where can be current at 0 voltage?
Let me explain. If there are equilibrium conditions, in this case, magnetic field cannot produce current. But if the system is driven out of equilibrium, there will be a current at 0 DC voltage proportional to magnetic field and chirality.
You talk about a spin current or a charge current?
About charge current.
Yeah, but I think your remark is again a bit related to this effect of I have definitely said that if you go out of equilibrium, there can be an effect of a magnetic field.
You're right.
So I think also if you the time I would be very interested in continuing the discussion with you, because my problem I have is that so here in our description of magneto resistance in the nonlinear regime, we know the parameters which is causing this. And we have basically it's actually the energy dependence of the tunneling, which is the factor which makes this possible. So if I have another physical, what you have to do is if you have if you want to look into things which you're mentioning, you have to think about a physical system, yeah, and then start asking the question which has both chirality and both magnetic field. Yeah, and then you can say, can I maybe generate a current, right? And I would
take a molecule between ferromagnet and normal electrode, apply AC bias, measure DC current, which will depend on chirality.
That is but that's the rectification effect, right?
Yes, in fact.
So again, I mean, okay. Let me.
But well, I made my remark, and if you're kind of interested, you can.
Yes, I'm interested. So please, let's continue this discussion after.
Thank you.
Let's just ask Jörg. You're next.
Yeah, hi Bart. I hope you can hear me. Very nice talk, and especially very nice modeling, easy to understand. If you go to transparency number 33.
33. Let me see where we are in this entire.
That's the CRR. This is the all-chiral spin valve.
That one, yeah.
Yeah, that one. So what I don't understand is that the MR is asymmetric, because this means that if you just exchange left by right-handed and right-handed by left-handed, you would get a different resistance. Yeah. And this looks like a parity violation.
Yeah. I think that's a very good remark, because we have assumed that these molecules are basically equal, right? So you're fully right in saying, and this is also, the MR, this is also, to be honest, something we have noted. And I think this is a very good question, and I think we should now really look into this. Yeah, because the whole thing is symmetric, right? I mean, what can...
It's really a parity violation that you have there.
Yeah, I think, but you have to be careful. I think the red one, no. This is, we should have a look. We have discussed it at some point, and then we thought that we had an answer to this, but I think we should look into this triggered by your question. So
as long as the molecules are fully symmetric, this cannot be, I would say.
If you are fully correct, right? I think you are fully correct. So we should check this, right? So please send me an email and we will check it immediately.
Okay, I'll do so. Thanks.
Okay, I think the next one is Marvin. Marvin, did you want to ask a question?
Oh, actually, I don't have a question. Probably I just pressed something by accident.
Okay, no problem. I'll put the next one. So Jonko, I don't know if you're next, if you had a question or not. Or maybe you just left the hand up, which could be the case there. Okay, so I don't think at this moment there's...
I don't hear you anymore.
Sorry, I think with this, there's no more questions. I don't think, I think some of them were just leaving the hand up without realizing that they still had the hand up. So I would like to thank the 300 of you that showed up. And I'll stop now the live streaming and here, and to thank Bart for a wonderful talk.